Hello chemists. Today we're going to be looking at redox reactions, and as you might remember, those are also called electron transfer reactions or oxidation reduction reactions. After we assign oxidation numbers to each of the elements on the reactant and product side, we'll look at what's oxidized and reduced, and then eventually we're going to balance. And this is new. We're going to use something called the half reaction method, and there's some tricks we used in order to help balance these, because balancing these in the traditional way by trial and error can take a very, very long time, and this trick really works well. So first of all, let's look at each of our elements and the charge that they take, what we call oxidation numbers. And there's two ways to do this. You can kind of use mental math, knowing that elements like oxygen always take a -2 charge when they're in a compound. So using your oxidation number rules, if oxygen is a -2 charge, we're going to try to figure out arsenic's charge. So down here I used a little bit of algebra to show that if I have 3 oxygens and each is a -2 charge, and I have 2 arsenic, and I don't know the oxidation number for arsenic, then I can set up this algebra equation, and since it's a neutral compound, it has to add up to 0. So many of you guys can do that math in your head, but if we just set this up as 2x equals 6, that means the charge on arsenic is going to be +3. So we have our oxidation number here for each arsenic is +3. And for nitrate, the charges or the oxidation numbers don't add up to 0. They add up to -1. So if we set up our equation, we get x plus 3 -2's for oxygen equals -1. So this tells us that our nitrogen is going to have a +5 oxidation number. So again, oxygen is going to be -2, as it usually is in compounds and ions, and nitrogen +5. Since this is an oxidation reduction reaction, something is going to be oxidized and something is going to be reduced. So we have to look at our products and decide which. So using our same rules, if we look at oxygen over here, there are 4 of them, and each one takes a -2 charge. Hydrogen almost always takes a +1 charge in compounds. And since I have 3 positive ones, and I have a total of -8 with the oxygen, that tells me that arsenic is going to have a +5 charge here. And as you can see, arsenic started +3 and ended up as a +5, so the charge is definitely changing. For nitrate, it turns into dinitrogen trioxide. So following that same logic, -2 for each oxygen, there are 2 nitrogens here, so each nitrogen is going to be a +3 charge. Also, you can see nitrogen has a +5 and is changing to a +3. So the next question, now that we have all the oxidation numbers, is what is being oxidized and what is being reduced. Now, you might remember that Leo the lion says Gur, so loss of electrons is oxidation, and it looks like the nitrogen is going from a +5 to a +3. It's going down in charge, so it's actually gaining electrons. If I look at arsenic over here, from a +3 to a +5, going up in charge means that arsenic has lost electrons. So arsenic is oxidized. And nitrogen is going from a +5 to a +3. So nitrogen is reduced. So I will erase this and we'll start our balancing reaction. For the remainder of this problem, we're going to balance this reaction using the half reaction method. So I've written the steps over on the right, and I highly suggest you keep a copy of these steps because it'll help you with these balancing tremendously. If you'll notice, I left the charges of the ions or compounds that are being oxidized or reduced. And the first step is to break this up into 2 half reactions. Now, one thing you want to realize about these reactions is that they're done in water. So we do a couple tricks here, because we're able to understand that in water we have an excess of H2O molecules. So we can use those H2O molecules in order to aid in our balancing. Also, because in water, and whether it's acidic, basic, or neutral, there's always going to be some hydrogen ions floating around. It might only be a few, but they can still be used in the balancing. And we also have hydroxide ions floating around. So in most cases, we're going to use water and hydrogen ions for balancing these reactions, because we understand that in order to balance our oxygens and hydrogens, that we might need to tap into some of the things that are in the solution. So for balancing H's and O's, we're going to, again, I call it a trick, but it's a strategy that helps us balance these. In order to split this into half reactions, we take the oxidation side, which is arsenic turning into arsenic acid, and we can just rewrite that down here. And our other half reaction is nitrate turning into N2O3. So when we look at this, there are no hydrogens actually on the left side. So that tells us that we're going to have to do some things in order to balance this. So using the first, the water here, actually, according to our rules, we're going to balance the elements other than oxygen and hydrogen first. So other than oxygen and hydrogen, we only have arsenic. And on the left side, we have 2. On the right side, we have 1. So just like in a normal balancing, we'll put a 2 in front of here to balance our arsenic. Now we have a different number of oxygens on each side. It looks like we have 2 times 4, 8 oxygens over here, and 3 oxygens over here. So in order to balance this, we're going to write in 5 water molecules. Let me create a little bit of room here. So now our waters are used, 5 oxygens plus the 3 here, give us a total of 8 on the left and 8 on the right. The problem is we have 10 hydrogens over on the left side now. And we only have 6 on the right. So using our ability to put in hydrogen ions in order to balance, 10 on the left, 6 on the right means we need to add 4 hydrogen ions on the right. So now our arsenic, our oxygen, and our hydrogen are all balanced. So after we do these steps, the last thing we have to do is put in electrons in order to balance the charge. For redox reactions, we have to have the charges balanced as well. If we look over here, there are 4 positives over here, and it's neutral. Everything adds up to 0 over here. So we're going to add 4 electrons on this side. So now everything is balanced. Everything on the right adds up to a 0 charge. Everything on the left adds up to a 0 charge. So our first half reaction is balanced, and we'll do the same for our second half reaction. First, we're going to balance the elements other than oxygen and hydrogen. There are 2 nitrogens over here, so we need to put a 2 in front of nitrate. To balance our oxygens, it looks like we have 6 oxygens over here, so we're going to add 3 waters to the right side so that we have 6 oxygens on the left. So 3 oxygens in the water and then 3 in the N2O3. And now with the 6 hydrogens on the right, we're going to put 6 plus H plus over here in order to balance our hydrogens. So there's 6 hydrogens over here, 6 oxygens, 2 nitrogens, 6 hydrogens over here, 6 oxygens, 2 nitrogens. The only thing we need to balance now is the charge. Since there are 6 positives here and 2 negatives, that means we're going to add 4 electrons to this side. And that gives us a total charge of 0 on the left. 4 negatives plus the 2 negatives in nitrate makes 6 negative plus the 6 positives here. Now, this example works out pretty nice because there are the same number of electrons balancing in the reaction up here and the same number of electrons balancing on the left here. So in this case, we are actually able to add these together and just cancel off the electrons. So when we combine our half reactions, we want to make sure we cancel our electrons. If this had 2 electrons over here, we would have to double everything in order to make the electrons cancel out. So when I bring everything down, I have 4 electrons. I'm going to write small to fit everything. 2 nitrate, 6 hydrogen ions, As2O3, 5 water. That's everything on the left side of the arrow. On the right side of the arrow, we have 2 of this arsenic acid, plus 4 hydrogen ions, plus N2O3, plus 3 H2O, plus 4 electrons. The first thing we might notice is that 4 electrons are common on both sides, and we are allowed to cancel things that are the same on both sides. So we definitely want to cancel our electrons because that's one of the main points in doing this. Also, we have 3 waters on the right and we have 5 waters on the left. So we are allowed to cancel all 3 of these, which will leave us with 2 waters on the right. Similarly, we have 6 hydrogen ions on the left and 4 on the right. So we can cancel off 4 hydrogens, and that will leave us with 2 hydrogen ions over here. And now it looks like we've canceled everything that is common on both sides. And when we rewrite this reaction a little nicer, 2 nitrate ions, 2 hydrogen ions, As2O3, plus 2 H2O. On the right side, we have 2 arsenic acid, plus N2O3. Now, if we count everything to make sure it's balanced, it looks like we have 2 nitrogens on this side, and we have 2 nitrogens on this side. And for arsenic, we have 2 arsenic on this side, and also 2 arsenic on this side. In terms of oxygens, I count 6 in the 2 nitrates, plus 3 in this As2O3, that makes 9, and then 2 in the water. So I get 11 oxygens on the left. And it looks like here we have 8 oxygens in the arsenic acids and 3 here, so we get 11 oxygens. For hydrogens, count 2 here, plus 4 here, I get 6 hydrogens on the left. And then 6 on the right over here. And the last thing we want to check is our charge. We want to make sure our charges are balanced. So everything is neutral on the right side, and with the 2 nitrates over here and 2 hydrogen ions, the charges add up to 0 on the left. So this is your balanced redox reaction using the half reaction method.